In the last video, we showed that the function r can be expressed as a function of theta in such a way. And before I show you why this translates to an ellipse, first of all, let us define what exactly is an ellipse in mathematics. So if we draw out the xy plane, we can define an ellipse using an expression like this. And so alpha and beta are both constants. People usually use a and b instead of alpha and beta, but I just realized I've already used the constant a to stand for the constants g times the masses, so that's why I'm just going to use alpha and beta. So this expression here will define an ellipse. So the set of points whose xy coordinates satisfy this relationship will actually form an ellipse. And you can easily show that this distance over here between the center of the ellipse and the side where it intersects the x-axis is going to be equal to alpha. And then this distance is going to be equal to beta. You can easily show that by substituting y is equal to 0. You will see that this point is equal to alpha 0. And when you substitute in x is equal to 0, you can show that this point is equal to 0 beta. And that's why you have these two distances. And you can also show that when alpha is equal to beta, what you're going to get is essentially a circle. So you can kind of view the circle as a special case of an ellipse where alpha is equal to beta. So now you might ask, why does our expression look nothing like this? So how on earth is this an ellipse? So in the next video, I'll show you how we can simplify or transform this expression into something like this. And so we'll do that in the next video. And before I move on to that, I just want to point out the fact that in this case over here, for this expression, you can see that we get an ellipse, and the center of this ellipse is going to be at the origin. Meanwhile, for this expression, the ellipse that you're going to get is going to be shifted to the left. So for this expression over here, you can see that we have this arrow r with a length of r, and then it has an angle theta, and then this function essentially tells us how the length r is going to change as we swing this arrow around 2 pi radians. And then as we'll show in the next video, when we rearrange everything into such a form, you will see that the ellipse that we're going to get is going to be shifted to the left. So the center of the ellipse is going to be somewhere over here. So you can see that it's different from this one. The center is at the origin, and for this expression, you're going to get a shifted ellipse. And then, of course, there's actually a special name for this point over here. Remember, this is where we placed the sun. So we placed the sun over here. It created a gravitational field which restricted the path of our planet. And this special point over here is going to be called the focus. And you can see that over here, we've created a distance of closest approach between the planet and the sun. And then we're going to have a special name for this distance. It's going to be called perihelion. And then this distance will be the distance of furthest approach. And this will also have a special name. This is going to be called aphelion.